Hi there, welcome to this lesson on electricity, this time specifically looking at the magnetic effect of an electric current. I am your presenter, Alex Nkumbi. Okay, so last time we were looking at the looked at the heating effect of an electric current. This time we want to look at the magnetic effect of an electric current. You must understand that electricity has several effects, and that's the reason why it is used in several ways. Okay, so just like the heating effect can be applied, like we said, even we looked at in the other lesson on the heating effect, we said it can be used in electric kettles, in electric cooker, pressing iron. The magnetic effect also has its own specific uses. Okay, now in this lesson we are not going to go as far as uses of magnetic effect of an electric current. We shall look at the following as our outcomes, and then the remaining stuff we shall do it in our next lesson. Okay, so the lesson outcomes are: we should be able to explain the magnetic effect of an electric current, we should be able to describe the magnetic field patterns around a straight and coiled conductor, then we should demonstrate force between two parallel conductors carrying an electric current, two parallel and anti-parallel conductors carrying an electric current. Okay, so with these outcomes set, let us straight go into looking at exactly what the magnetic effect of an electric current is. Okay, so when current flows through a conductor, the magnetic fields develop around that conductor. This is called this phenomenon whereby when a conductor carries an electric current and then magnetic fields develop around it, is what we call the magnetic effect of an electric current. And we know that a magnetic field cannot be seen, but its effects can be felt. So we can demonstrate this by making a current, a carrying conductor to pass near a plotting compass, or simply by making a wire carrying an electric current to be placed near a plotting compass. Okay, so the needle of a plotting compass is actually a magnet. Okay, so the needle of the compass deflects each time the circuit is switched on. Okay, we can see it in this. Actually, this diagram is just to show us the arrangement that can be made to show the magnetic effect of an electric current. Okay, so we have a compass there with a needle which is a magnet with a north pole and a south pole there. Okay, and then we have a current, and this current must be a low voltage and high current current, because the supply must be low voltage and high current. The reason is we want to see the effects of an electric current and not the effects of the voltage, and therefore to have the profound effect we need to have high current. Okay, so when the circuit is switched on, the needle is seen to deflect in that direction. Okay, so the reason is because the needle of a compass is a magnet. So its deflection actually indicates that there is a magnetic field that develops when the circuit is switched on and current is flowing through that conductor. And the phenomenon can be demonstrated in the clip below. So we can actually demonstrate, because here this is a still picture, you can't actually see what is happening. So we can demonstrate what I've just talked about in this clip here. Okay, so before we play this clip, look at the following. In this diagram here, we have a battery with a positive terminal here. So current will originate from the positive terminal, pass through. So this wire is made to pass through this paper, and that paper, it is sprinkled with some iron filings. Now those iron filings have arranged themselves in a circular pattern because of the influence of the magnetic field that develops around this wire. Okay, and then it will come like this, and you can see here that the direction of current is shown by the red arrow there, and this is the direction of the field that will develop. But don't worry about how we are going to tell the direction of the field. We shall use the right hand grip rule to see how we can determine the direction of current, and you shall see what will be happening each time we change the polarity of the battery, meaning when we change, the positive goes there, the negative comes here. Okay, so in this arrangement you can see that that's how the field will be moving. It will be moving around the conductor in a circular path and in the anti-clockwise direction if current is going up. Okay, and then we can reverse the polarity of the battery by making the negative to come this way and the positive to go up like that. And then you see the field is now reversing and current is going down because it's originating from the positive and going to the negative. Now we can use the right hand grip rule so that we understand how to tell the direction of the magnetic field. So according to the right hand grip rule, and you can see here, when you grip the conductor, the thumb must be in the direction of current, and then your curled fingers are showing the direction in which the field is. So the field is moving in this direction while current is going up. Okay, so when we change the polarity, this one comes down, meaning that the negative is now here. Current will be moving down instead of moving up. And then you should also change the direction so that your thumb points downwards. Okay, so let's see how that will go, like that. So you can see your thumb pointing downwards, your fingers have changed direction. Let me just repeat that part so that you see clearly. Okay, we just repeat the part where the thumb is down. Okay, this is the part I want you to understand clearly. Okay, so you can see the thumb, when the thumb is down, the fingers are curling in this direction, indicating that current is now moving. Magnetic field pattern is now in the clockwise direction when current is going down. So it is very important for you to remember how to use the right hand grip rule in order to tell the direction in which current is moving and the direction in which the magnetic field will be around that particular conductor. Alright, so we have actually explained what the magnetic field, the magnetic effect of an electric current is. We can now proceed to look at the magnetic field pattern around a conductor. We will start with a straight conductor, then we shall look at a curled conductor, or we shall look at a loop and also a coil. Okay, so magnetic field patterns around a straight and a coiled conductor. So you can see, like in the previous case, if current is going up, passing through this paper, then the magnetic field around the conductor will be in this direction. Now, this is arrived at using the right hand grip rule. Okay, so that's the magnetic field lines. These are magnetic field lines, and this is the direction of current. Okay, what about a loop? If we had a loop like this one, we have current entering, and then again it passes through this paper and then passes through this paper going down. So current is going up and then it goes down. So using the same right hand grip rule, you can see here that current is going up, and therefore the magnetic field patterns will be in such a way that they will be in a clockwise, in an anti-clockwise direction. And then on the other side, the same current which was going up, now it is going down. So the magnetic field patterns, when we now turn the thumb pointing down, the fingers will point in a clockwise direction, so it will be in that particular direction. So we can easily tell this by simply using the right hand rule. Okay, now we go to the field pattern of a solenoid, or simply a long coil. So we have a coil in this particular case here, and it is switched on. As you can see, there is a positive terminal here, negative here. So current is flowing in this particular direction. So you can even see that it is moving like that. Here it's moving up, 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 up. So it's moving up on this side of the coil, but at the back there it's dropping. Okay, so the magnetic field pattern can clearly be seen here. If these arrows represent the direction of field patterns, then they are originating from here and moving to this part. Actually, when we use the grip rule here, we can even tell that this is the, remember about when we talk about the polarity of a magnet, where the fields are originating from, that's the north pole, and where they are terminating into or entering, that's the south pole. Okay, so how does this work? Let's see. In this particular case, we will also be changing or rotating the pose. We'll be changing the pose and see what will be happening to the magnetic field pattern. And we shall use the right hand grip rule as well to be able to tell the direction of current and the direction in which. So you can see here that the current has been reversed. Now the positive is here. So when the positive is here, it means that but then you have to be careful. You should look at also the loop. If this loop here, the first one was passing on top here, then it means current would have been going up. Okay, but it is passing behind the coil, this folded paper or any material that we fold to make the coil. Okay, then let's see. When we proceed, we want to look at the grip. So here I'm just demonstrating the changing of pose. So I mean the changing of terminals. So now you can see when we use the right hand grip rule, the thumb actually points in the direction of the north pole of a magnet. This coil is behaving as a magnet. No wonder why we use it when we are talking about the magnetic method of, the electrical method of making a magnet. So this is where the north pole will be, where the thumb is pointing, and the curling of the fingers is showing us the direction in which the magnetic field, in which the current will be moving. All right, so from here, let us see. Okay, so let's see. So we can also change the polarity here. If we change the polarity, what happens to the right hand? So you grip the coil from behind like that, because current is now moving like this. Okay, so let me repeat that part so that we see it clearly. Okay, let's see the part where the current of the polarity of the coil is reversed, so that we change the way we grip the coil. So you can see here, when the positive is here, current is moving like this. So here it will be moving down. So that's why these fingers are curling down, and the thumb is pointing in the direction of the south pole. Of the north pole. Please be careful here. When we are dealing with a coil, the thumb is not telling us the direction of current. Okay, it's different from the case where we are dealing with a single wire. Okay, in the case of a coil, the thumb points in the direction of the north pole, or it simply tells us the direction from which the magnetic fields will be originating from. So they will be originating from here and entering here. Okay, all right, so let's now look at how we can draw this pattern in an actual drawing. Okay, so here we can see that if this is a solenoid with current moving up like this, if you use the right hand grip rule, then we know that the north pole is here. So that's where the field patterns will be originating from, and they will be entering into the south pole, which is here. So originating from the north pole and entering into the south pole. Okay, so far we have looked at the patterns of magnetic field lines on on a straight wire, on a loop, and on a single loop, and then on a solenoid. This time we now want to look at the last outcome of our lesson, which is the force on two wires carrying an electric current. Okay, so we are going to use this simulation here so that we can understand what happens to the two conductors when they are carrying current, and we'll look at a situation where they are parallel, that is carrying current in the same direction, and anti-parallel where they will carry current in opposite directions. So in this arrangement we have a cell here, although it's noted as a battery here, or we can have a battery, we can have many cells, but we have a single cell shown, and we know this is the positive, so current will originate from the positive. So in this particular case it will be moving like this, and then it will go like this when we close this switch here. Okay, so we will look at a situation where the first situation we will look at is where current here is moving in this direction, but you can see here that it will be moving in that direction. So they will be actually antiparallel, or carrying current in opposite directions. Okay, so let's see what happens to the two wires in terms of the force that they experience. Here we are looking at the force. We want to demonstrate the force between two parallel conductors carrying an electric current. So as you can see, when we close the switch, those two conductors will repel each other. Okay, so they will repel each other when they carry current in opposite directions. Now we want to look at a situation where the second situation is where you can see there is a change here. Now when current originates from the positive, when it reaches this junction here, some of it will flow through this conductor and some of it through this conductor. So current will meet here, and then, so in short, in this arrangement, current is passing through the two conductors in the same direction. So the two are actually parallel. So the currents are parallel in the two conductors. So what happens to them? When we switch on, you see that there is attraction, and you can see the field patterns developing around. Okay, so from that demonstration, we see that when two conductors carry current in opposite directions, they repel. When they carry current in the same direction, they will attract. Okay, so we can actually show this by way of drawing. So if this is a conductor carrying an electric current in this direction, and that is an upward direction, and then this one is carrying down. So if you use the right hand grip rule, for the situation where current is going up, then we know that the field will be in the anti-clockwise direction like this. But here where the current is going, when it's going up, the field is in the anti-clockwise direction. When current is going down, the field is in the clockwise direction. Now what will happen is that the direction of the field lines will be in the same direction. So this results into repulsion here. So this wire will move in this way if it was free to move, and this will move in this direction if it was free to move. Now if we change direction of the second wire so that it also carries current in the upward direction, let's look at the field patterns that develop. If we use the grip rule, this conductor will carry current will have magnetic field patterns in the anti-clockwise direction, and even the second one will have magnetic field patterns around the wire in the anti-clockwise direction. So what will happen is that at this point here, the two field patterns will be moving in the opposite direction, and therefore this will result into attraction. So the two wires will attract themselves if they carry current in the same direction. They will repel themselves if they carry current in opposite directions. Okay, and I'm sure we have looked at the outcomes we set for this lesson. To go through quickly, the outcomes we had were to explain the magnetic effect of an electric current, which we have done. Then we have described the magnetic field patterns around the straight and the coiled wire. We have also included a single loop. And then we have demonstrated the force between two parallel conductors carrying an electric current. Okay, so with these outcomes covered, I want you to just look at this exercise. Okay, so let's start with exercise 1 actually. So exercise 1 is from the specimen paper for 2016 pure physics. So the figure 7.1 below shows a solenoid made from wire wound around a plastic cylinder. So this is a plastic cylinder, and then there's wire wound around this plastic cylinder. We are given the polarity of the wire. The conductor is positive terminal, this is negative. The question I want you to answer from here is a current in the solenoid produces a magnetic field. Okay, so on figure 7.1, draw the pattern of the magnetic field lines inside and outside the cylinder. Okay, remember we looked at that part there. So I want you to do that. You draw for the inside and the outside. That is what you are supposed to do. And then let's now look at exercise 2 or question 2. the figure here, the figure below shows two wires carrying an electric current. The figure below shows two wires carrying an electric current. The switch is closed. Okay, so if the switch is closed, this switch here, we have two wires, X and Y. This is X, this is Y. They are connected to the same battery here, and then there's a resistor here. So when the switch is closed, it will be a complete circuit. The first question is, show the direction of current along each conductor X and Y. So you indicate by way of drawing using arrow to show the direction of current. Then B, indicate the pattern of magnetic field around each conductor X and Y. So you indicate here the circular move by using a circle showing the direction in which the field lines will be. And then C, state whether the two conductors will attract or repel. So that's all that I had for you today on this lesson, the magnetic effect of an electric current. See you in the next lesson concerning the same, but now we'll be looking at applications of the magnetic effect of an electric current. So please do not miss, especially if you are writing pure science, because questions on the magnetic effect of an electric current are very common in pure science papers. Thank you so much.